Section 2.9. Determining the change of the internal energy and introducing a new state function, enthalpy. First, delta U is equal to Q plus W. To change the internal energy of a system, either Q or W will have to be non-zero. In an adiabatic process, Q is 0, then delta U is equal to W. In an isobaric process, there's no change in volume. There's no expansion work nor compression work. Delta U is equal to Q. And in this case, we put V in the subscript to emphasize that the volume remains unchanged. In an isobaric process, pressure is a constant. To ensure that the system pressure is a constant, P external will have to be equal to P. Otherwise, the system pressure will change until it becomes the same as the external pressure. So again, the isobaric process is also a reversible process. Therefore, du equals dqp plus dwp in the isobaric process. dqp is copied here. dwp is negative pdv because pressure is a constant. Then pdv is equal to dpv. Why? dpv is equal to pdv plus vdp in calculus. vdp is 0 because pressure is constant. And then we can just rewrite this equation. Again, dqp minus dpv is du. Therefore, dqp is simply dpv plus du. Now we have the sum of two exact differentials. We can put them together. It's going to be just the differential of u plus pv. So now you can see, in an isobaric process, this dqp is equal to the exact differential of u plus pv. For convenience, we just define a new state function to be the sum of u and pv. That state function is enthalpy H. Therefore, the H is equal to dqp, delta H is equal to qp. What does that mean? That means if a system undergoes a isobaric process, the change of the enthalpy of the system is equal to the heat flow. Now, how to calculate delta U and delta H in an irreversible process? Because U and H are state functions, one strategy is to design a reversible process that connects the initial state and final state of that irreversible process. Why? Again, U and H are state functions, so we can design whatever processes we want as long as they have the same initial state and final state as the irreversible process. And then we can compute the change of U and H. In short, it can be expressed as these two functions. As long as we have the same initial state and the same final state, it doesn't really matter if the process is reversible or irreversible. Delta U is going to be the same. Sometimes, if a process involves the change of too many variables, for example, the P, V, and T of an ideal gas all changes, then we can design a two-step process in which one step is isothermal, therefore temperature is constant. The other isobaric, therefore the volume is constant. And then we can compute delta U for these two processes easily. In an isothermal process, we say it's delta U sub T. The isobaric process, delta U sub V. For ideal gas, delta U sub T is 0. Why is that? For ideal gas, the potential energy is 0. The kinetic energy is proportional to temperature. So, if temperature is constant, then the kinetic energy is constant. Therefore, the change of kinetic energy is zero. And also, it's an ideal gas. Therefore, the change of its zero potential energy is always zero. Therefore, delta U sub T is zero. How about delta U sub V? Well, in this case, isobaric process, that means work is zero. Delta U sub V is Q sub V. Q sub V is simply the integral of the isobaric heat capacity dt. So, for ideal gases, the change of the internal energy depends only on the temperature. If temperature remains constant, delta U is zero for ideal gases. If the temperature changes, we just need to integrate CV. To compute this Q sub V, it's also delta U sub V, it's also delta U. How do we compute the change of enthalpy? Well, again, we design a two-step process. The first isothermal, the second isobaric. For an ideal gas, we learned that the internal energy is zero. The internal energy change is zero in an isothermal process. Well, delta H in an isothermal process is also zero because H is U plus PV. And we learned that this U doesn't change. And also PV doesn't change because for an ideal gas, PV equals nRT. If temperature is a constant, then the change of nRT is zero. Delta PV is zero. Therefore, delta H in an isothermal process is zero. Enthalpy now only depends on pressure. Enthalpy only depends on the temperature. If there's no temperature change, there's no enthalpy change. What if there's a temperature change in the isobaric process? Again, this P in the subscript stands for isobaric. In this case, very simple. Delta H in an isobaric process is equal to Q sub P. And Q sub P is simply the integral of Cp dt. So in summary, for ideal gases, the internal energy and enthalpy only depend on temperature. If the temperature is constant, then the change of U and H are both zero. If the temperature changes, then delta U is integral Cv dt. Delta H is the integral of Cp dt. We just need to know the initial temperature and final temperature to compute delta U and delta H for ideal gases.